Hello everyone, welcome back to Module 1, Week 1, Lecture 3. In this lecture, we'll talk about the typical failure mechanism. In the previous lecture, we talked about non-destructive testing is to identify the integrity of the material structure or components or the system and quantitatively measure the property of the material without causing any damage. So one of the primary reasons is to predict the future service life. So therefore, it's very important to understand, what you need to know and what to test, where to test. So therefore, it's very important to understand the typical reasons for material structure failure at the mechanics level. With that, this lecture will cover some of the primary reasons for materials of structure failure, that's including discontinuity or the defects, and we will spend 1 week to discuss elastic and inelastic mechanics, and then we'll talk about linear fracture mechanics in week 2. So this is in week 2, and we'll briefly overview buckling, fatigue. We will spend 1 week, week 3, on creep. And this is very important property for a lot of civil engineering materials, even including the concrete. And then we will touch upon some property on the corrosion. So let's begin. So as we talk about the non-destructive testing is to identify discontinuity or the defects and evaluate the performance of either material or the components or structures or systems without causing any damage to the original part. Again, I want to bring up this is important definition. NDT is very, very diversified field ranging from materials level characterization such as X-ray diffraction, photoluminescence, and computed tomography, CT, or scanning electron microscope, all the way to system level or structure level discussion, such as distributed optical sensor arrays. So in this class, in our class, we'll be more focused at the materials and the structures level with certain exposure to system level testing and assessing. So we're more focused on how to test the materials and how to test the larger structure components. And we will spend at the course number 3, we'll spend probably 1 week to discuss the distributed optical sensors and how that purpose serving with IoT sensors. So first, let's take a look at what we call the intrinsic discontinuity or defects at materials level. Here is a schematic of any material, which we know fundamental building elements, it's atoms. So if we consider each of this is one atom, and in between, that's your chemical bond, right? That's your lattice. So a perfect material will each atoms in their position, and then that's nice connection between these atoms with your lattice, and then the distance between atom A to atom B, we call it the lattice distance. So sometimes we know there is an intrinsic defect, right? What happens if the chemical bonding between two atoms broken? It's your lattice is broken. So therefore, as you see, in a perfect world, if I apply a load, in this case it's tensile, so the load will be nicely distributed through the material. However, if the lattice is broken in this case, so therefore your load will be concentrated in this area, right? As you can see, we have the load will be heavily stressed in these two atoms. And so therefore, will be a weak spot. Discontinuity is very easy to happen in the material at the fundamental building blocks level. That's what we call intrinsic defect, right? Which is inherently located at the material during the original production process. For instance, here is some scanning electron microscope picture to show you how the materials orientation. As you can see here, we have a materials is what we call polycrystalline. You have some orientation which this direction, and then you have orientation going to this direction. So therefore the mechanical property will be very different on each of the plane. So it's a similar case here. As you can see, with this is atomic structure of the zinc oxide on sapphire, right? This is a transmission electron microscope, and this 2 nanometers. So each is of this is a couple angstrom. So therefore you can see polycrystal zinc oxide. So we have one plane going to this direction and another plane going this direction. So this is what we call the green boundary. So as you can imagine, right, this will be one of the weaker spot mechanically. So one of the NDT's purpose is to identify discontinuity at the materials level, such as the picture has been showing here by using transmission electron microscope or scanning electron microscope. Um, this slides, I would like to show you some defects during the welding, right? So this is the welding part. As you can see, we have the voids here, right? So this is the radiographic, right? X-ray, and as you can see clearly, there is a voids here. So therefore, the defects can happen during the manufacture process, right? Or machining parts or the structure parts. That will be leads to premature failure. And in this slide, I would like to talk about the third type of the defects, which is called service-induced damage, right? On the left, we can see a computer chip going through this cyclic thermal loading, so therefore your wire bonding of the conductors or the wires, in this case could be copper or some other conductor wires, and then that could be easily broken. So on the right is the bone structure, right, of the human bone, and then the hip implant cyclic loading from the walking. So as you can see, this is because of long time of the fatigue. So therefore, damage can be induced from the cyclic loading, such as thermal, such as mechanical processing, such as corrosion, creep, that can induce some defects. So it's important by using some non-destructive or non-invasive testing methods to understand the damage, such as X-ray diffraction or CT. Fatigue is one of the most common failure mechanism for structure material in civil engineering, particular pavement, right, your concrete, your asphalt material, because of their service life. So this is typically caused by the cyclical stress, right, such as your traffic, the car, the vehicles, and that type of the stress typically cause the progressive and the localized structure damage and the growth of the crack, as shown in the photo on the right, right? This is a regional crack has been caused by the cyclic loading over the time. As we can see, the crack start to grow, right? And then the scattered and eventually will cause the material structure failure. And it's important to point it out that stress is much lower than your yield stress or the tensile stress. In other words, if we're looking at, we had the sigma, right? If it's in tensile sigma and your epsilon, right? Stress strain curve, and then you have your material, right? Going through the perfect linear Hooke's law, and then reach a little bit of plateau, and then you pick it up and get to the ultimate stress, right? And then you fracture. So this is your sigma T, right? So the stress at fatigue, which will show by S and N curve, this is not sigma epsilon curve, that stress will be much lower than the yield stress, than your ultimate stress. So two stages of the fatigue. At the beginning, you have the crack, which we call crack initiation. The crack initiation is a material structure change in response to applied stress. And then that is also we call pre-existing crack of the material. What really dangerous, so it is a concern when the materials start have the crack. However, if the crack grow very slow, it's not a major concern. What really concern is with this is crack grown, but also grown at a very quick speed, right, during the cyclic loading, and then we call that fatigue on the fracture surface. For instance, as you can see here, this is aluminum crank arms, which um, has been showing, right? So you have an original fatigue crack has been showing at the dark color part. And once we reach to the certain threshold, and then this crack will be grown exponentially, and then that's to lead to a sudden fracture. So the material break, or in this case, is this part of the aluminum crank arm will all of a sudden break into the couple pieces. And so therefore, what really need for us to be concerned is during this crack growth time, right? So which we'll talk about in the next class, week 2 in the linear fracture mechanics. So the characterization of the fatigue is what we call the S and N curve. S is the amplitude of the stress, and versus N is the number of the cycles at the logarithm scale, right? So basically, S-N curve is the stress applied. So basically, S-N curve is the stress amplitude versus your number of cycles to failure at log scale. Has been showing here at the bottom. We can see an S-N curve for the brittle aluminum, right? So this is the ultimate tensile stress as a 330 megapascal, right? So that's if you do this sigma, right, and epsilon. So ultimate tensile stress here is the 300 megapascal. However, depends on how many cycles I'm going through under this sinusoidal stress. You see the stress to the ultimate failure is way lower than this particular number, right? Than your ultimate stress. So this is typically done by a coupon testing, right, under the fatigue machine, and usually is 2/3 of the tensile strength, and the number of the cycle to be failure is counted, right? So this is important, and how many cycles can we get? More detailed information you can check on this link below. So how to characterize fatigue? Let's quickly review the information you learned probably in some other classes before. Fatigue in life, right, it's determined by the number of the stress cycles to cause the failure at a specified stress level. Fatigue limit, right? The definition of the fatigue limit is the maximum value of the cyclical stress below which fatigue will not occur for an infinite number of the cycles. And fatigue stress is that magnitude or the amplitude of the stress, right, at which failure will occur for the specific number. For instance, you could have 10/6, right, 10/6 cycles in this case, and then you may have your fatigue stress is 200 megapascal, something like that. So more detailed testing can be found in ASTM E606, ASTM E647, or ASTM D6588. It depends on what material testing, right? and your loading speed. So this type of the testing standards typically will give you the very specific information how to fabricate your testing coupons, and then how many cyclic load cycle you're going to go through, and your loading speed and such as that. Other than fatigue, creep is another type, very typical failure mechanism for civil engineering materials such as concrete, epoxy, composites, steel, right? So what is creep? Creep by definition is time-dependent deformation under a certain applied load. Or in other words, any solid material, they have a tendency to move slowly or deform permanently under the influence of the sustained loading condition over the time. So therefore, creep is definitely a time-dependent property. And another thing is creep. How can induce a creep, right? First, you need to have a very sustained load, right, for a long time. And another thing it can induce a creep is temperature. For instance, we see, composite wood at the higher temperature, they tend to start deform, right? They tend to start buckling. So a temperature, a epoxy, when you heat it up, right, the epoxy start becoming softer. So this can induce creep. And there is a three stage of the creep, right? So if you look at the creep curve, so this is your strain, this is your sigma, this is your T, right? So this curve is indifferent than your tensile strengths, your linear. It's at the beginning here, you have this elastic region, right? So this is a linear response. And then once after the material go through that, you get into this creep region. So at the very beginning, we call primary creep, and that started at a very rapid rate and slow down with the time, and then go through this relatively uniform, right, uniform stage, and which we call it the secondary creep. And then you get into, this will be getting into the very dangerous part, that will get into your accelerated creep rate, and then you get in approaching to the material break, right, the material fracture or the ruptures. So we will spend the 1 week, week 4, oh, I'm sorry, week 3 to jump into the details to explain the creep behavior and how we calculate and quantify the materials deformation under certain sustained stress. How to characterize the creep, right? And how we understand the creep is, creep characterization is done by measure the dimensional change accurately as constantly high temperature or constantly loading or the stress condition, right? So here is the testing setup for concrete, for instance, per ASTM C512. You steel, you're looking at the ASTM E1457. Um, and again, creep mechanism is very different between the metals, plastic, rubber, or concrete. Again, it's because of the material's property, right? So you could have this what we call fracture material, or you could brittle material, or elastic material, or ceramic material. They are very, very different. So therefore, depends on what type of material, you have to go through different ASTM standards, which we'll cover again in week 3 in this class. Here is one of the very unfortunate example I would like to show you how important to understand the creep behavior and to avoid the accident like this. This has happened in 2006 on July 10th. The 12 ton of the concrete panel has been falling from the 4-point channel in Boston. So everybody probably know Boston Big Dig project, right? So this is one of the concrete panel on the ceiling. Unfortunately, it fell and killed the 2 passengers. The primary reason was really on this creep type of a failure with the anchor. So they use the epoxy, and then the anchor, several anchors was embedded in the epoxy, and then holding this concrete panel in place. However, the epoxy has this creep behavior. So over the time, creep has deformed, which we call the stress relaxation. So therefore, the bolt was ruptured, and then this entire panel has fallen. So as a civil engineer, it's very important to understand all those type of behaviors of the material, right? It's hard to imagine very solid material such as concrete, and we will have a significant deformation over the long time as well, so which we will discuss in week 3. Buckling is another type of typical structure failure, particular for the columns, because of the slenderness of the column. So as can be seen here, if you have a concentrated uniaxial compression, right, and the column has insufficient flexural stiffness, so they tend to bend for one direction. So that's what we call the buckling. And the critical load of the buckling of the any columns are determined by the equation as being listed here. PCR equal to pi squared times A over the E, or modulus of the material, modulus of elasticity, times K. K is what we call the curvature mode or stiffness factor, which we will explain in a minute in the next slides. And L is the length, the column length between the pinned ends. Are its radius of the gyro. So as you can imagine, or easy to understand, the buckling issue of the columns is definitely directly correlated or dependent on what we call the slenderness, right? The slenders of the beam, and then which is, or the columns, which is your length over your smallest radius, right? So we call this A over 16, and then we call it a long beam or long column. And if it's a smaller, and then will be short. So as you can imagine, the long column and the short column definitely have a very different buckling behavior. Okay, so the R is a radius of gyrotation. Gyrotion or gyro is equal to I, moment of inertia, and divided by A, the cross of the air. Now let's discuss this K factor. K is so-called stiffness factor or the curvature mode, which is really a constant that based on the end condition, how the column being fixed, right, in the particular structure. So the K factor is determined by how the end has been fixed. For instance, if both ends pinned, what is pinned is means you have a degree of freedom of the rotation. So it's not really completely free, but you could rotate it for this direction or this direction. You could have a rotation. So if both ends is pinned and the K equal to 1.0, and if you can have this range to all the way if one end is pinned and then one end is fixed, and then you could have a K equal to 2.0. So it depends on how the end fixed, we have different K value. That's something I would like to point it out. So here is some example have been shown you, right? And then not only just the column can buckle, the beam can buckle as well. For instance, here are some wood beams, and that buckling is really coming from the thermal loading during the drying condition. As long as you have a uniaxial compression loading, right? And then when this have a very long slender issue, and then you have this buckling. And here is a clearly example to show the buckling of the columns. as we can see here, right? So for the columns, they never yield, right? It always buckled, as you can see, the concrete, and then the rebar still hold together. However, there is a significant displacement, right? So this leads to catastrophic failure because you have such a large displacement, so the entire structure will be buckled. So other than the buckling, corrosion is another typical structure defect or materials defect, and that can be detrimental, right? Either to be concrete or steel. In this case, we have been showing is the sulfate reduced bacteria on untreated sewage, right? That make a very big damage to the concrete pipes, and then the sewer pipe, as you can see here, is a significant thinning of the thickness of the pipe. And as we also know, the seawater um, has a very strong effect to corrosion. So for instance, when concrete is exposed to seawater, there's a significant corrosion. So the cover of this steel rebar has been um, completely vanished, right? And then this is typically attacked by magnesium chloride and a sulfide ion and the carbonation in the seawater. So, and other than seawater, acid rain and often leads to the corrosion, which significantly reduce the concrete or steel compression strength durability, right? As being shown here with different pH, as we can see, you know, with the pH 1.5 after 90 days, there's a very clearly honeycombing in the concrete structure. So as you can imagine, the completely, you know, the compression strength and the durability will be reduced. Here is another example to show you concrete reinforcement going through the corrosion, right? The exposure of the reinforced steel to chloride ions is a primary corrosion. And then as you can see, some of the steel has been corroded, and then some of the corrosion starts to showing up in the concrete and leads to the large crack. Corrosion can lead to catastrophic failure if it's not being addressed properly. For instance, here is an example I would like to show you in December 2017. There is a very big bridge called the Georgia Foot Bridge collapsed right in Czech Republic. Um, and so this is actually a 30 years old bridge, the 30 years old. So it's not a very new bridge, 30 years old bridge. And then the major reason was collapsed is because of the concrete reinforcement structure corrosion as being using here. So the rebar has been completely exposed after, you know, fracture surface. As you can see, it's clearly is corrosion leads to compression strength has been reduced, so cannot take the load. What is really interesting here, I would like to point it out, just an anecdote. It is very interesting. So this bridge has been instrumented with the sensor to measure the deflection 3 weeks before the collapse. So 3 weeks before the collapse, the engineer actually installed multiple sensors on this bridge to measure the deflection and at every 2 minutes interval. So this is very interesting. It's not exciting, interesting, it's sad, interesting. What really needs to learn the lessons here is what you need to understand what is to be measured, right? So in this case, the corrosion is such a significant contributor, and what we're looking at is deflection. So again, um, the knowledge of the NDE is very important, right? The inspector's knowledge, where to measure, what to measure, right? What you're looking for is very important. It's not only about what type of the tools or the methods you're using. So that's one of the take-home message from this particular accident. I would like to point it out. So in summary, right, the role or the purpose of the NDT or NDE depends on, you know, what you're familiar with. In this class, I will just call it NDT. So NDT provides evaluation methods for the material components or the system level quality control and safety assurance. And it can provide qualitative, sometimes it's very quantitative data for engineers, the technicians to analyze, evaluate the quality of sustainability for service at the materials, components, or system level. One thing I would like to point it out or bring to your attention is NDT expert really needs to work with the fracture mechanics and the structure engineers or material scientists together to solve the problem, right? Some of the NDT experts are very good at testing methods, data processing, analyzing. However, you need really working with a structure engineer and fracture mechanics or material scientist to understand where to look at, right? And then what to look at, right? For instance, that Georgia Bridge, as we just pointed out, and they had sensor was installed and then measure deflection data at every 2 minutes interval, and the millions of the data has been processed every single day, and unfortunately 3 weeks later it's collapsed. So, and it's always important we as a community to work together. So with that being said, the next week we'll talk about fracture mechanics and then part of the structure mechanics in the next 2 weeks. So in this way, we can build a very solid foundation and a knowledge base for non-destructive testing methods. So thanks for your attention for this video, and the coming next is the case study. It's also a term paper I expect you to complete.